Recording in progress. Not bad.
Vielleicht sollten wir den noch.
Hello everyone. Today I'm very happy to welcome our two guest speakers, Professor Andreas Feller, faculty at the CISPA Helmholtz Center for Information Security and professor at the Saarland University. And on the other hand, we have Norman Pitek, postdoc also at the Saarland University. And I think we just going to straight start with the presentation of Andreas Feller, who's going to talk about notebooks and how to write them and test them.
Great. So thank you very much. Thank you for having me here. Interesting question. How much time do I have?
1.5 hours, probably? An hour, something like that?
1.5 hours just for me? Okay, good. So then if you knew that you had only 1.5 hour left, what would you do? Well, I'm giving talks, so let's see what we can do here. Okay, so I have ample time in the world, so I can tell you about anything in the world, but I'll try to keep this as short as possible, such that we have more time for questions from all you folks around here or on Zoom land, whatsoever. So this today is about, the talk today is about effective notebooks. Thank you so much. And this is about, well, it's a bit about doing data science, but it's also about a bit, well, how to do research. And it's a bit about how to code software. I just said the S word. Did you hear the S word? Software. Okay, just checking. There's people who immediately come up with a delighted face when I say that. Yeah, I see that. I see that. Is that true? All men in this room are super happy when I say software. Is that true? Just checking. Just checking. Okay, good. People with hoodies like software. Okay, I get that. Okay.
People working for Lars Kronske like software, I guess.
People working for Lars Kronske. But we're going. But I'm trying to bring all of this together. Even if you don't like software at all, even if you hate programming whatsoever, I'm going to show you a bit in here. So how are we going to start this? Actually, not at all, because it doesn't work. Okay, let me try that again. That's interesting. It doesn't work. Okay, good. So here we go. No, it doesn't work either. Okay, good. Now it works. Thank you so much. So a bit about myself. This is the CISPA. This is the Helmholtz Center for Information Security. This is where I come from, in the beautiful Saarland. Saarland is 1/3 of the size of Berlin, and number of inhabitants. It's 3 times as big as Berlin, and I think in area we definitely have more forests than other stuff. And generally, you don't hear that much from Saarland. Whatever broken elections, broken trams, whatsoever, things generally work, and we don't talk much about stuff. The interesting thing, but CISPA is actually one of the most impressive things in Saarland, because it's a huge investment by the federal government into research, into computer science. It's a research center that is set to hold up to 1,000 researchers, all in computer security and related areas. And it is a Helmholtz Center. Helmholtz, these are the institutions that take care of big scale research. And CISPA, in the 3 years, in its first 2 years that exists, already has managed to propel itself at the top of worldwide rankings. This is CS rankings. This is a comparison of all computer science departments in the world. If you want to look where your individual computer science department is standing there, well, check out where Humboldt Berlin is sitting, and CISPA is here at it is at the very top with 18 faculty, and I don't even know what this number is. I think it's 36 top publications per year from 18 faculty, which is a record. But the other ones, what's next? Georgia, Carnegie Mellon, Cornell, ETH Zurich, you heard of that one, Northeastern University, University of Illinois, and all of the other ones. This is all North America. So even in there's no other European university except for ETH Zurich that comes close, and we are obviously very proud of that. Actually, there's a reason why I'm in Berlin, because on Monday we had a nice event where the governor of Saarland, the Minister President Tim, gave a big lauding speech for CISPA and how important this was for Saarland and the world. Okay, good. So all of this is computer security, which is not so much your business. It's a bit of my business, but I'm working on other stuff in here. In the past 3 years, my two main projects were actually book writing. And I've written 2 books. One is a book on fuzzing, which fuzzing is a technique for generating inputs for computer programs. Hopefully inputs that cause your program to malfunction, to crash, for instance. It's amazing with that in some cases, just a few characters suffice to break your software once and for all. And this is a book on systematic techniques and how to do that. And once your program has crashed, for instance, after fuzzing, then comes so-called debugging, which is we want to figure out why it crashed and we want to fix that. And in the debugging book, I put together a couple of automated techniques that help you fix the bug soon and as soon as possible. Okay, so yeah, good. That great professor at some research institution writes books. Yeah, sure. This makes the news, right? So of course, who else does that? Good. Okay. Do we have that? No, of course not. Okay, good. This was the boring part. The more interesting thing is actually the way I write these books, and this is where we get a connection between writing, computer science, and data science. Well, data science is a part of computer science, but I hope so at least. Okay, and the reason why all these things come together is because I am writing these books not with whatever Microsoft Word or LaTeX or whatever. Say as an academic, this is LaTeX, this is Word, and well, I have no idea what the other things would be. No, but I am one of the ones who write these books, and it's using some other tool because I'm writing them with Jupyter notebooks, and Jupyter notebooks is actually something that was developed to do data science, such that, and these are documents that allow you to put together code, like your favorite code editor if you do programming, but also text. That is, you can also put in text here as using Markdown, using LaTeX and whatnot. And important also, you also see the output of the code. And the output of this code actually can also be graphic output. So, which is what it makes so great for data science, because you can immediately visualize all sorts of things, come up with great interactive diagrams, making them coming up in 3D and analyze everything, maps to all that. This is what makes it super powerful. In this example, I'm using something as boring as a class diagram, which for software engineers like I am, of course, wow, I can do class diagrams. Wow, that's super cool. Yeah, if you do data science classes, okay, let's not talk about these at this point. But for me, this is a great means to combine all of this into a single thing. Because if I am using LaTeX, well, then I have to copy and paste my code into some verbatim environment. Here we go. And I can definitely not execute the code because if I don't, we can go and execute that code. And I also, if I want to draw diagrams in LaTeX, it's not really meant for that. You can either draw the diagram using a lot of funny \something commands, which is super painful, or you just use some external tool to do that. But then problem is when you're using standard ways that all of these individual sources, your text, your code, your diagrams, you don't know whether they actually are in sync with each other. You can always change one and without changing the rest. This can lead to mistakes. Whereas in a Jupyter notebook, if I change the code, then the diagram changes accordingly, and I can even make sure that the code, that the text which I write actually also is in line with the code, because I can even generate the text automatically if I want to. So this is lots of fun. And if you are writing even something like a thesis, for instance, actually doing so in a notebook can be very interesting, because it gives you plenty of stuff that you wouldn't find anywhere else. So there's the concept of literate programming, for instance. Literate programming meaning that you actually explain to a reader what you're currently coding. This is an old concept. This goes back to Donald Knuth, by the way, the inventor of tech and therefore LaTeX, and many other things. We have time. Donald Knuth is the guy who writes a typesetting system because he's unhappy with the way his books are typeset. So he starts writing a typesetting system, and then he writes code for building great font libraries and everything, and then he can produce nice books. So that's the kind of person whom I really admire. But and one of his ideas is actually to compose text and code together such that you get something that is easy to read. This is something you can do you can easily do in notebooks. You have Markdown for a very simple highlighting of text. So if you want to write bold text, italic text, whatsoever, you can simply put underscores in front, and then at the end of a name, then the document is highlighted. And you can also put in formulas, of course, for academics. This is super important. So you can also create, this comes in LaTeX syntax, and then you can create a very complex formula to be integrated right within your document. You have outputs and examples that become part of the document. We had that already. And you can even integrate interactive elements, which you also can program yourself if you want. So you can even integrate some, say, interactive quizzes right into your text. And then if you're a reader, then you can ask the reader, is this the correct answer? Please check the correct answer and everything. There's even folks who do exams this way. So you just send a Jupyter notebook to your students, and then students have to follow quizzes or solve programming examples, and you can then easily follow what all of them are doing. And these are, of course, all things that do not exist in things like Word or LaTeX. Well, and you can do a quiz in LaTeX, but you can certainly not make it interactive. That would be stretching the concept of a book. I mean, you could put a QR code in your book and then have the QR code check whether you're correct or not. But that's complicated. Okay, so this is all fun when you're writing books with that. And also, well, at least from my perspective, the ability to visualize data, the ability to produce nice outputs. So this is standard data science. You visualize distribution, but you can also create your own output formats. This is an output format which illustrates the concept of so-called statistical debugging. This tells you where the bug is. The redder line in here is the more likely it is to contain a bug. So yeah, it is indeed line 6 that has the bug. Or you can also create, and of course also have nice formulas. We had that already. Or again, nice interactive distributions, graphs of all sorts, class diagrams and whatnot. Some of these are visualization which I produced myself. So I have code in there which does all that. Or you can also, of course, use plenty of stock visualizations, and there's great packages in all languages, in Python, in R, in Julia, all available for that. So this is all fun. Question is, who in here wants to write a book? Okay, good. I'm not talking to the right people here. Maybe out there in Zoomland, but if you want to write a book, yeah, it's could be a fun option. So I'll give you an example of what this whole thing at the end looks like. For this, we'll just be happily switching over to the end result in here. Let me see whether I have it. Here we have it. Wonderful. So this is the latest book. This is the debugging book. And here you see already how it starts. It starts off with a video of myself explaining the whole thing. Sure, so do this with a regular printed book or PDF, whatever, you're not going to get this. And then it explains how things work. Oh, there's even some Twitter integrated in here. So you can do all sorts of interactive stuff that are simply not found in regular books. And now you can actually go through the menus in here and whatever, for instance, go and read the introduction to debugging. That is how to find things out. And all of these things are also illustrated in videos. So plenty of fun. All of these things that go way beyond what a regular book can do. So, and yes, this book uses Python all day long. Python is a great language for beginners, and it's simple enough such that you can also treat it as pseudocode. And I'm happy to also use Python in my examples because, well, it does the job, and it's also the prime language for Jupyter notebooks. So this is fun. So you can do this, and you can write a book. And so, but the fun thing is, you know, we are here at the university, right? Okay. Sometimes I wake up in the morning, don't know where I am. Okay, university. Also here at the university, also here at the Humboldt University, people write software, of course. However, it is not necessarily the job of the people who write software over here to make money with said software or to ensure that it has a long life, whatever. But the main point of academics is we want to do our experiments and possibly with software, then we want to publish this whole thing and then we're going to forget about it. Okay? Which is why software, if it's written by academics over time, often resembles something like this. Some extremely complicated machinery that evolved over dozens and dozens of years, and where again dozens of people have contributed at some point, and where it's actually pretty difficult to find out whether and why this whole machinery actually works. So this here is actually one of the accelerators, if I recall things right. So well, if you're watching this on video in a couple of weeks, I'll be sure to please correct me if I'm wrong. So this is what some software would look like if we would visualize it. Another way to visualize this is imagine this room in here. And on this side, you have 500,000 switches that are all distributed across the wall. On this side, you have a couple of lamps. And if you press this switch, then this lamp goes on. You press another switch, then another lamp goes on. You press a third switch, and then all lamps go out and do not turn on forever. Well, that's an explanation, actually. Thus, on top, you have all the cables between these switches lying around in the room somewhere, or going from up there to down there, or from going up there to down there. And then there's little tags on these cables telling, do not touch under all circumstances. So this is what software also looks like, okay? So academic software often is a total mess. I've talked to people who are writing climate prediction software, for instance. This is being done in Hamburg, where they have the climate center. And yes, they have some huge Fortran programs. Fortran is an ancient language for computer scientists. This is like let's say Sanskrit or Old Greek, which people try to avoid if they can in their daily interactions. And every year, and once in a while, there is some new PhD student who adds a couple of lines to that thingy in order to improve the climate prediction a bit further. Whatever. Last year we had clouds, better cloud modeling on how do clouds affect climate predictions. This year we're going to look at the first 20 centimeters of water, how that affects the climate. And next year we're going to look at clouds, how they reflect themselves in the water and how that might possibly affect future climate. And this whole code is a total mess because over the years, Every time there's some other student adding some other stuff to it, and nobody really knows how it works anymore. The only good thing is people know that it works, because if they feed all the data of the past 100 years into the climate prediction model, then it tells you something like that today in Berlin is going to be sunny, above 7 degrees. That's good, and you can use this for validation. So, and the more precise it is, the better it is. And the assumption is, of course, that it keeps on being as precise as it is in order if you run this if you predict what the weather is, what the climate is going to be in 100 years. But yeah, there's lots of knowledge in these things, and nobody knows exactly how to extract that knowledge again. Nobody wants to do that either, and life is complicated. And it's always cheaper for a new PhD student to add their whatever 30 lines of code to that modeling, rather than to take these hundreds of thousands of lines which nobody understands anymore and actually rework them from scratch. Okay, so this is academic prototyping for you. The state of software as produced by universities is not always in the best shape. There are examples of software written by the university folks who actually have done a good job. Any one of you having a mobile phone, maybe? Of course, yeah. Anyone here using Android, for instance? Okay, I see it. Good. Android runs on Linux. You may have heard of Linux. Okay, Linux was written by a guy named, a young student actually, named, young Finnish student at the time, named was Linus Torvalds. And he built the first Linux kernel based on another system which was called Minix. Minix? You ever heard of Minix? No, you don't know Minix, of course. And Minix, interestingly enough, was a project written by a university professor in a book that contained plenty of code, namely how to write an operating system, together with plenty of code, with plenty of text explaining how one does that. And Linus Torvalds actually took that book and took that code and started from this book building his own operating system. So, which means that the code that you're using on your mobile phones every day was originally created by some university professor. I'm super proud of this. We should actually name this Tannenbaumix, because Andrew Tannenbaum was the name of said professor. Yeah, well, there's other folks who say it should actually be named GNU Linux or whatever. Well, Linux was the name that started. And maybe the first one telling that anybody should name this Tannenbaumix, but yeah. Okay, so there are examples, but you have to keep things small and you have to keep them well documented, and then you have a chance at others. But not only do we have trouble with complexity, we also have trouble with documenting what we're actually doing. So what I'm having here is a notebook. So this is a real world notebook, of course, yeah, right. So sure, we are working along, we're happily working along, we're taking notes of things, and well, some of us have handwriting, some of us like to doodle, and we are happily putting all of this together, but the next morning, can we still understand what we actually wrote down here? That's complicated, right? And sure, while you may be conducting your scientific experiments, you may also be taking notes whatsoever. That's all fine. It's good, helps. But will you be able to understand what you have jotted down the next morning or in a week? Or can anybody else understand what was actually going on here on this thing? Let the gray levels, okay, rain, run. No, might be a diary or something. Okay, good. If you're a scientist, you are supposed to take notes about your experiments and all, and what comes out of this. And here's another example. This is a notebook from Otto Hahn, but actually they have been here in Berlin, not very far from here. This is Otto Hahn, the physicist who, among others, let me think, discovered fission. Was that Otto Hahn? Please check. Anyone with Google, thank you so much. One of the greatest physicists of all time. And this is his lab book. Okay. And you can see that he very carefully wrote down all the experiments he did. And he also very carefully wrote down all the results he got from beginning to end. Because he knew, well, at some point I'm going to need all that, or others may be needing that in order to find out whether my experiments were done in the right way. If you are studying natural sciences, biology, pharmacy, chemistry, physics, then you learn how to do such a lab book. Because if you do not properly document the experiments that you do, then chances are that you can make horrible mistakes. If you screw up and whatever, you take the wrong strand of mice into your experiment. If you screw up and mix up multiple petri dishes for your experiments, whatever, these can all have very. What you're doing is expensive. It can actually kill people. Okay, so you have to be very careful in your experiments, documenting everything that you do. Yeah. Do computer scientists work that way? Did anyone in their computer science studies ever learn how to do a lab book? No? No, you don't. No. Because computer science, is this an experimental science? No, of course not. Do we do experiments? Experiments. Well, we do experiments when we are debugging, right? So we need to, maybe we want to figure out why something failed. This is actually where a lab book can also be helpful, but now you're doing data science. I'm doing data, so imagine for a moment I were a data scientist and now I'm trying to figure out, is there actually some relationship between A and B? And here I am with my computer and I'm taking this data set and working with this other data set, and then I'm doing this and I'm doing that. And all of a sudden I find a correlation between two things. That's cool. So I jot that down like this. And then I continue. Well, if I have something like this on the left side, and this is where I keep my results and everything, I will be in deep trouble later on ever replicating this stuff and understanding what actually just found. No, you can also do this in a very systematic fashion and actually jot down, this is what I did, and this is what I found. Okay? And this is also, lo and behold, where tools like Jupyter notebooks, now getting back from the written notebooks to the electronic notebooks, can be a tremendous help. Because in a Jupyter notebook, which is actually one of the ideas of the whole thing, is something where you can write down, hey, let me do this experiment. And then you enter the appropriate code, and then you find something, and then you write down your next thing, what you try next, and there you go. Because a Jupyter notebook has all the means for you to actually write down what you're doing and proceed one after another. Interestingly enough, one important thing about a lab book is also it cannot be altered. In modern words, this is a blockchain. Well, just joking here. No, the thing is, you cannot retrospectively go and say, okay, this was a different result. I got something else in here. Okay, if you do so, this would be falsification of research, which is a bad thing. Well, with Jupyter notebooks, that's not exactly the case because you can always eradicate all the experiments that you did, which opens up a can of worms because, in fact, you can actually say, oh, this didn't work. Maybe what happens if this didn't work as I expected? If I remove these elements from my data set, will I be able to get my p-value correctly? Oh, what else do I need to remove from my data set? Oh no, finally I have significance. Wonderful, I have something to publish. Yeah, sure. And then you remove all the earlier things that you did. Well, you also just falsified things, but well, will people ever notice? Who knows? Long after you finished your PhD, long after you published your paper. And in the meantime, there's going to be some scientific finding around which you thought was relevant, but which in fact is not. Okay, so let's get back from these academic notebooks to, to today's topic. Is it true that I just did 30 minutes of introduction? I'm so sorry about that. When we do the video later on, I'm going to speed up. Okay, so what I'm going to tell you today is I'm already through more than half of my slides at this point, so no worries. I want to come up with a couple of checklists that help you who are working with notebooks, who are doing data science, to become better scientists by making your research, by putting your research in a way such that it can be replicated and reused by others. And for this, I am going to borrow a couple of tricks from software development, the tricks that professional programmers use to actually create software that lasts, create software that can also be reused by others and understood and expanded by others in the future. Actually, I'll be going to total extremes here, because I will first show you a few simple rules that are very easy to follow. And then I'm going to give you examples from my daily routine, which is at the total extreme end of how you can do things, which is how you could do things if you were a professional programmer obsessed with software quality. I understand you're not. So, but at least a couple of very, very basic things to keep you busy. Okay, so in fact, I'm going to talk about 6 best practices today. And these are how to automate things, automate the execution of notebooks, automate the creation of data sets, automate everything. I'm going to talk about how to use version control such that you always have a backup of your artifacts, and such that you can track any changes that were made by you and by others, and also enables you to collaborate. I'll talk about how to systematically test things. I'll talk about how to abstract things such that, again, you can use your notebooks in any context. Finally, and then we're already getting into more advanced topics, how to modularize things, that is, how to turn your notebooks again into packages that can be used. And finally, how to document things. This again is very easy, how to make sure that people will actually understand what's going on. And by the way, also how you yourself can understand what's going on 2 weeks later after you did something, because that's about the time frame, that's what the time it takes for you to no longer remember what you actually did here. And we're going to start with our first checklist here, and that is automation. All of these are checklists which you can actually use to go through your current coding practices, even the simplest stuff, and just check, is this something I can easily do? So, that's rule number 1 in here is people must be able to execute your code. You have a notebook, you have whatever piece of code, people must be able to run this. Because if they cannot get this to run, they will not be able to use it, to extend it, even to understand what it's doing, because they cannot see the results. That's very, very bad. That's the minimum that you must have, which means that you also need to leave instructions on how to execute it. And in particular, this is a particular problem with notebooks. In a notebook, you can easily execute first this part, and another part, and another part, and another part in between. You can execute things in arbitrary order. And which means that afterwards, after you've executed things, it's not always easy to find out in which order you actually executed things. And if you have a notebook of someone else who has done this style, well, this is the equivalent of this scribbling notebook where you scribble anywhere on the page. No, you want to have this in a decent order from top to bottom, and this is also how your notebook should look. If there's anything that your notebook needs, I need a particular data set in order to run. Well, then make it part, make this downloading and unpacking, make this also part of the notebook. Or at least leave instructions on how to do this. If there are specific commands that need to be used, you can also make these part of the notebook such that people can, when they execute the notebook starts by downloading the data set from some public source, and then it does whatever computation is. And yeah, in particular, well, if you work with Python, you will typically make use of lots of extra packages, notably, well, for instance, for doing machine learning, for doing visualizations, whatsoever. The Python language changes as well over time, gets extended. And once in a while, one of these developers out there happily changes the interface to their packages such that your code also needs to be adapted. Yeah, and this is bad because then anyone who wants to reuse your code will suffer from the same problem. And this is why it's helpful for you to rerun your code once in a while to check whether it still works. And by the way, this is also something that can be automated. Okay, so this is just a few basic rules, not very complicated to follow. And because it's so much fun, let me give you a brief look behind the scenes on how this works for me. So this is the book, this is the final result. This is what we have. And this is what one of these chapters actually looks like when I am working with it. So you see, now here we have a Jupyter notebook that actually does everything. And you see, yes, I'm also making use of other packages in here. And there's a bit of documentation and explanation. And this is a chapter that actually starts with importing data. Actually, it downloads the version data for the book in order to analyze it later on. And what I'm having here is I'm having code that sets up all these things. It finds out what the current name of the project is. I give instructions on where the repository can be found. And then it automatically loads down all this data. It actually runs for, if you run it, it starts with running for 5 minutes, downloading all this data. I'm also giving instructions on what this data looks like. I give information in here. And after downloading all this data, that's when I then start doing some analysis on it. And in the end, I'm getting some neat visualization in here. Here it is. This is a visualization of actually the individual parts of my book, in which a color indicates how frequently a particular notebook has been changed. This is the slicer notebook. I think it holds the record in here. And this is how I show, yes, this has had 47 changes. This part of this notebook here, this is just an error message actually, has had 2 changes over time. This here, chapters.makefile has had 30 changes over time. So I'm doing a bit of data analysis in here. And this chapter is fully self-contained. When you execute it, it automatically does everything. It downloads the data set. It does all the visualization from top to bottom. And I can rerun this at any moment in time, and it should work. So all I need to do here is I do clear all outputs, which is something as a data scientist you would typically be terrified of, because you immediately lose, oh, I lose all the visualizations I just had. Well, it's not that bad because it can just go and restart the whole thing. Why can't I go and just restart the whole thing? That's new to me. This is new. Okay, good. Let's try that one. Okay, I didn't see that before. That's interesting. Okay, good. And then I can do run all. And then, yes, everything is recreated from scratch, and I can do so at any point in time. Well, Unfortunately, now we have to wait for 20 minutes until all the analysis automatically runs again. So this is one thing when we talk about automation. And I have to say I'm a bit more excessive than that, because also the creation of the entire book is fully automated. At any point, I can go and use an automatic build system to, no, sorry, that's the wrong button here. At any point, I can use an automatic build system to actually go and remake the whole book from scratch. This is called Make. This comes with a Make file. This is one of the oldest build systems in the world. It's ugly, it's painful, but so are all other build systems too, so I don't care much. And I can just go, oh, I can actually say make help. Then it gives me instructions on the things I can do. And here I can go, for instance, I can say, I want to say make a book, for instance. It even creates a PDF. I don't know whether this still works, but I can also go and do make chapters in here. And then it automatically determines all the individual commands that need to be done, that need to be run in order to regenerate the book from scratch. And of course, there is another command that then happily also publishes the book on its website. So while this is happily running, a third point in here, just because we have it, this is the project page for the book. And on this project page, I do have something which is called actions. And in these actions, these are things that run. These actions are tools that run automatically every once in a while. Actually, they get rerun every time I make a change to the book. And every time I make a change to the book, every time I'm making a change to the book, then there's a couple of tests that all run automatically. And here, for instance, I can see that my last check that I did, I think this was 4 days ago. Yes, 4 days ago. Then I can see that all of these individual checks which I installed here also all work. Can I check this? Can I see anything in here? This is a question. We should be able to. No, I can't. Okay, good. Not today. Oh, I need to sign in to view the logs. Oh, yeah. Oh, complicated. Okay, here we go. Could be it. No, I'm not going to save that. Security key. Oh, very interesting. YouTube. Oh no, I'm not going to go through it. I'm so sorry about that. Okay, good. So what I wanted to show here is that this is the last point here. The notebook is actually, all of my code is being rerun at all times. And I therefore can always make sure it is up to date. All this happens in the background because I am the producer of a book of code that my students use. And I'm interested in having everything up to date at some point. As I said, this is probably going to be totally excessive for you, because well, here you are. I'm doing this. I'm just doing this one analysis here. So why should I care? And this is right. You don't have to automate it to that extent. But you know, you're scientists. You want to have impact. You want to have other people look into what you're doing. You want to have other people reusing your particular approach. Okay, and then it is actually important for you to actually maintain your code and keep it alive, such that others will always be able to use it. There's big movements in making such software and such notebooks citable, for instance. And so if others are using your code, your notebooks, then they put up citations, and then your citation index rises, and then you'll be the king of the hill, simply because you wrote a particular piece of code that not everybody uses, and yes, it's your method. Okay? And this is something you want to enable. And if someone says, oh, I found this beautiful notebook by Professor X, and I download it and it doesn't run. Well, there goes the citation, of course. No, I'm not going to debug this right away. Okay, good. And if there's no project page where I can leave a bug report, then well, I'm not even going to invest time in that. I will just jump to Professor Y or Professor Z or PhD student X, whatsoever. Okay, so pays off. Okay, this was automation. Something we already saw on the project page, which I just had. The project page is essentially a repository for my work, and it allows me to save. Essentially, it allows me to save an infinite amount of versions in my repository. And this then again allows me, this then again gives me backups for free, as many as I like. Because if you use version control, you can always look up what are the individual versions of my code, of my notebooks, whatsoever, of my data set even. And I can look up, yeah, what did my code look like 5 minutes ago? What did it look like yesterday? If your code no longer runs today, but you remember it ran yesterday, and in between you made a couple of changes, well, then it's a good thing to have a backup in your repository, and you can even look up which changes you actually made. Okay. If you do not have that, well, then it's all up to you manually searching for the one USB stick in which you saved a copy notebook.back or notebook.back.back, notebook.back2, notebook as sent to my supervisor.back. Okay, well, maybe you're lucky and you remember all these individual versions, and maybe they do have a timestamp. Maybe you still have that USB stick, that's all nice. Maybe you don't. Okay. But you know, if you have a repository, a central repository where everything is stored, everything is so much easier. So this is crucial. You use version control if only to have a backup of whatever you're doing. Nice thing too, as soon as you have a repository, you can always check which changes you made, and you can also go back to previous versions. You can even do so selectively. If you have such a repository, all of a sudden you can also collaborate with others, meaning that you don't have to send individual copies, again, supervisor.back, whatever, to your peers who then make changes, and then they come back, and there you have plenty of individual files with different dates. And, oh man, what is that stuff? No, if you have a central repository, makes it super easy for others to collaborate. It also allows third parties to submit bugs. Well, maybe that's not what you want, but you want to know about your bugs, because if you don't even know about the bugs, then well, you miss another chance to have scientific impact. It also allows others to extend your code and submit improvements or extensions to this, so you can make the whole thing more collaborative. And then you find more co-workers who are also interested in what you're doing. Maybe you can do joint work. Well, that makes life easier again, because you are working on something exciting, I hope. And if others find that exciting too, then you can join forces and make this even bigger and greater. And you were the first, so you can lead a new movement that will then finally. Okay. Well, maybe. And having a version control system, like the favorite system of choice these days is called Git. There's two big sites, GitHub and GitLab, which make it very easy for projects to set up accounts, store stuff. It's all free for students now, definitely. Oh, by the way, Git was invented by Linus Torvalds, the guy who built Linux, who was inspired by this other academic guy named Andrew Tannenbaum with Unix. Yeah. Everything is connected to everything. Okay, so because we can, just also give you I'll give you a short insight about what my project repository for this book looks like. Do we have it here? Should have stayed with Safari or something. Here we go. So this is GitHub. This is the GitHub repository for a book. And actually, the page that we saw before, the pages of the book actually also are hosted by GitHub. So I don't have to pay a thing for that. Thank you very much, GitHub, for hosting all that. Otherwise, I would have to go to my employer and ask them to actually host this. And then I have to go through procurement and whatnot, and all of this is complicated. See, downside of having an interactive book is you don't get paid for it. You don't sell copies. Sure, I could sell ads or something on that page or something. Yeah, that could be fun, but don't do it. So these are all the individual folders in here, and you can see that it's a very, very substantial project. and actually anyone can do that. I can also look up here what the individual parts of the book are here. So here's 404, which I changed last month. I can't even remember that. What was that mean? Here's something which I just changed 4 days ago. Yeah, you can always look up what was the last change. And that's something I can do, or that's something that others can do too. Here's the readme.md. This is the original. Oh, this is actually rendered already. Very nice. And I think I can even look up individual. I can even look up individual changes in here, what was made. But I can also do so right here in the middle. Oh, still working. Very interesting. I can also do so right here in the middle of my code, because as soon as I change something, let me just enable a special view here. 1 second. Here we go. Yeah, breadcrumbs. Oh, sorry, not breadcrumbs, but I want to see the minimaps. Where are we? View appearance. Thank you. Minimap. Minimap, here we go. That's good. Thank you so much. This is something I don't want to see right now, so I'm going to turn this off. So this is my file in here. And as soon as I make any change in here, this is me vandalizing my own code. Ah, wonderful. There we go. Then I can actually already see that something has changed, because here on the left-hand side you see that there's a change that has occurred, and now I can make more changes just as I like. But the neat thing is that I can actually see that in here there is a file that just has changed. So let me get back into this thing. In here I see changes that were made. And I can now look up which are the fail files that have been changed. And I see here that the file of the introduction to debugging has changed. Where is it? Okay, I don't see it. I don't know where it is. Where was it? Okay. The important thing is, at any point I can press this very button that allows me to go back in code, and then I can simply revert all the changes that were made. So I can always go back to earlier versions. I can also look up what the individual changes were made. Here I can see the timeline of the individual changes that are made, and you can see here that over time that not only me but others too have made changes to that, and I can also look up every single change that was made. Here's something. Here the red code is code that was deleted. The green code is code that was inserted. And at any point, I can always track back whatever was changed in here, which is very, very convenient. Okay, I need to think about getting back. I need to think about removing this. This is me vandalizing my own code at some point. I'm going to do this right afterwards. Okay, this is a bit about using version control. Next thing is testing. If you do research, and you make changes to your notebooks and all, you want to make sure that you do not accidentally break things. And even while you are developing code, you want to make sure that you are still on the right path. Now there's multiple ways to do so. The first way is, well, you simply look at the results and find out whether they are correct or not, whether they make sense or not. Human way of doing things. That's perfectly fine. But it's something that you cannot automate. And because you cannot automate it, then this means that you have to look into your results again and again, whether they're still doing the right thing. And there's a nice tool that allows you to check whether your functions are still doing the right thing. And this tool is called assertion. An assertion is a way to state that I am now expecting a particular result, and if this result is not as expected, then execution immediately stops. It's a great tool for debugging and finding errors, and it's also something that you can make very good use of while programming and also while doing notebooking. Again, I'd like to show you an example in here. So this is not very complicated, fortunately. So let me get into one of the notebooks in here. This is a classical example for assertions. It's a function that computes a square root. And it starts with an assertion that, well, it's supposed to compute the square root of x, of a number. And it starts with an assertion that says x must be greater or equal to 0. So it checks whether it is not accidentally invoked with a wrong number. And at the end, we also check whether the result is correct. That's also something you can very easily do. This computes the square root in the number y. And at the end, we check whether if we take y, the square root, and if we square it, multiply it with itself, then we check whether this is actually close enough to the original value that we put in. This close enough is defined by this epsilon value. You could also say simply y times y equals x, but since there is the possibility of rounding errors, such an assertion may actually occasionally fail. This is how you use assertions. And actually, if I go through the book, there's 500,000 assertions in here that all check whether the program is still doing the right thing. Let me just go into some arbitrary other chapter in here. This is a chapter that is not about assertions, but about slicing, which is a debugging technique. And here I even have a special function that does nothing but doing assertions all day long, more assertions, more assertions. This is all assumptions on individual values in here. And with these, I can document whether things are still correct or not. I can even, let me see whether I find this in here. Oh yes, I can even go and use this in order to check whether my program is doing the right thing. Let me see whether I have that in here. Yes. So let me just go for any of these in here. Debugger, how do I open this thing? Is that the right thing? No, that's not what I want. Oh, is that it? Good question. Here we go. No, wrong button in here. Yeah, here. So, oh, I was in the wrong file. That's it. Okay, no, that's not what I want. Second. Yeah, okay, I get it. Thank you so much. Here we go. Debugger, wonderful. And I am searching for assertions. Yes, there's plenty of assertions in here. And here's assertions that actually check whether the tool which I'm showing here does the right thing, and it checks whether whether the output is actually correct. It checks whether the tool that I'm using actually wants no further inputs in here. And by having these assertions in here, I can always make sure that the program which I'm running in here actually at all times does the right thing. I'm still having comments in here. Let's go for this one. Okay, good. Here we go. Wonderful. So here's the book. This actually shows how to build an interactive debugger where we are stepping through. And if I run this code and these assertions automatically are executed, I at all times can ensure that while these assertions hold, I can make sure that the tool that I'm actually using here does the right thing. Because otherwise, if I didn't have these, I would run into trouble soon. Because at any point, the examples which I'm showing off here could be doing the wrong thing. And if I didn't have these assertions in here, then there would be the risk for big trouble ahead. Because then all of a sudden the text would no longer fit the tools, or maybe the tools would just crash, would produce wrong results, and I wouldn't notice that, which is a bad thing to have for a text. Okay. Coming up next is abstract. This is again a couple of simple coding ideas here. If you have any constants in your code, notably as data scientists, You want to give them names such that people understand where they come from and what they're meant for, what they're meant to be. If you invoke some if you invoke some classification function with magic numbers 0.1, 0.35, 0.56, you want to understand what these values mean. You want to understand what they are. So it's much better to have a symbolic constants for that. You also want to set up your code in an ideal way, such that others can reuse it without having to change everything, without having to search where to change things. So having a section at the beginning in which you configure the whole thing, in which you say, this is the name of my data set, this is where to find it, and these are the parameters which I'm going to use for the rest of the execution, is very helpful, because then people know what things they are allowed to change and which others they're not. If you are more advanced, you can even go and say, okay, I'm going to turn my code into a set of functions instead. Functions allow you to use a particular computation with arbitrary parameters. So others can make use of these functions and use them again, possibly copying them, or possibly even making use of your code directly. If you are an advanced programmer, you can also make use of object orientation and use classes for such purposes. This allows you a very great amount of extensibility without having to change original code. You can extend and change behavior without having to change the original code, which is very useful. But that's something that, that's something that for good reasons comes at the forefront, because these 3 points beforehand are more important than that. In my code, and I'm not going to show examples in here, I'm using plenty of functions. And for every function, I'm giving an example on how it works. I'm defining the next function, and I'm giving an example. And I'm using functions all over the place, because these functions are pieces of code which I want and which I can reuse in other contexts and other notebooks. And while we're talking about this, I can also talk about modularization, which means that at some point, you not only want your notebooks to be executable again from others, but you also want to be able to reuse individual parts of it, maybe to do a similar analysis on a different data set with different parameters, whatnot. And then you need to set up and then the idea is to have a piece of code that is unchangeable, or more precisely, that can be changed only by you. You are the maintainer of the whole thing, but which can be invoked in various ways to suit the requirements of every single user. And the idea here is that at this point, you leave the notebook space and instead go into the Python/R/Julia space. You use regular programming environments or text editors to write Python code. And this Python code is built on the code that you use, that you copy over from your notebook. And you turn this into a bunch of functions that you can invoke again and again, and which you then again invoke from your notebook to show how it works. Okay, so your notebook typically is at the end of the food chain, so you have a couple of individual packages that you write in Python. And likewise, at the end of the food chain, at the very top comes your notebook, which makes use of all that, and where you show how to integrate all that. And these separate program files, and again, is something that you can also turn into a reusable Python package, which you also can publish as such. So make this my 10 favorite data science functions, something like that. Maybe the name is still available, and then you can place this on a server, and then people can actually go and install this. Pip install whatever Maria's best data science functions. There you go. And then they can write from Maria's wonderful data science functions, import, yada, yada, yada. And then they can make use of your code, just like you right now make use of whatever from PyCharm import and so on. Same thing, except that it's your module. Actually, this is open for everyone. So anyone can publish such modules, which actually is a bit risky from a security standpoint. But yes, if there's something that you find, this is something that you want to make available to others, that's also something you can do. And finally, this is something that I do. You can also go and import notebook code into your own notebook. When you get here, I have a notebook, and now I want to make use of these functions that I defined in this notebook, and I want to put this into this other notebook. Then you can import a notebook like you import in the same way that you also go and import Python files, for instance. This has the advantage of your code still being able to come up with extra text, with documentation, with examples and everything. The downside, however, if you use this in a non-discriminating fashion, is that all of your notebook gets executed at once. And if your notebook, like the notebook which I just shown you, takes 20 minutes to execute, then importing the other notebook also takes 20 minutes, because if it runs all the examples, that's a bit tough. So you have to come up with ways to separate the functionality from the actual examples, how you're using that. And that at this point, it becomes a bit murky, because you actually want to have these examples close to your code. So for this, we do not yet have an ideal solution. For my own books, I solved this the way that I wrote my own import function, which actually simply imports all the constants and all the functions, but leaves out the individual examples. Well, I am an experienced programmer, I can do that. But if you are just trying to get your notebooks to work, then one of the 3 earlier alternatives is easy. So, and we are slowly getting to an end here, and then up for you to ask questions. So, last part is documentation, and that's maybe the biggest advantage of notebooks over any other form of coding. So this is where I can say, I'm a data scientist, I use notebooks, I can document my stuff much better than any programmer out there. Except that most data scientists don't, which is the pain. Most programmers don't either, so but it's the whole pain, because that's when you have your code, whether it comes as a text file or as a notebook or whatsoever, if it doesn't explain what it's doing, then you're stuck. And if all your variable names or function names are just 1 character long, then you're even more stuck, because not even the identifiers tell you what the code is doing. And this is exactly how, like in the introduction, when you have these 100,000 of lines of Fortran code, and where everyone who wants to start with that first has to understand what's actually going on. This is the really nice thing about notebooks, that you actually can go and explain things, and you have all the space between individual code fragments to say what you're doing. And the neat thing is that it doesn't even take much time. You see, when I'm doing some data analysis, I'm actually writing down my thoughts as I have them. And I'm doing another analysis, and I'm writing down what I find as results, and I'm doing the next thing. Because very much like writing down things in a lab book, in a lab notebook, this helps me organizing my scientific progress. And at the end, I end up with a notebook that tells me, I did this, I did that, this came out, this is why I thought this is why I did this next thing, this is why I did this next thing. And anyone in the world later on will be able to read my thoughts and to see the results of my experiments and find out whether I was on the right track with all my experiments, with all my results. That's great. When I'm building something, I'm doing the same. I'm explaining, well, I say I am explaining to the reader how I do things, but at the same time, I'm explaining things to myself. And while I'm explaining things to myself, I actually begin to wonder, is this a good thing to do? Yes, this makes sense. So I'm laying out my plan, what I want to build. Then I'm building one small part of another. I'm trying out whether things work. So I'm actually using usage examples for every single function, which at the same time also serve as tests. And this is how I happily create an entire, not only the code, but actually an entire document that tells me and that tells others what is this code actually doing. And this is how I realized that this is how I then get this junction, this fusion between documentation and code, and at the same time, also teaching material in the end, because once I've explained things to myself, well, then I also will be able to explain it to others. And this gives me, this kills many birds with a stone. So I do have material for teaching. The students have material for learning. They can execute the code. I have code to share. I get a reputation as being a great programmer whatsoever. Well, all of this. So teaching, coding, presenting, it's all in one single package. Okay, good. Do you as students have to do this too? Well, things are, right now you are doing an experiment. And you're running these data, and you're running your favorite data science analysis. And here you go, and you find out, oh, this is super interesting. I just found this thing. And here's a notebook, in which you eventually came to a result. Okay, good. Write a paper about it, whatever. 6 months later, you're starting to write your thesis. Be it whatever, bachelor's thesis, master's thesis, PhD thesis, whatever. Okay. And then you remember, oh, I had this result. But then you have to explain how it came to be. Okay? And then all you have is your pieces of code where you went through, and you have to understand, what on earth was I thinking at this point? And then it takes you hours or days just to figure out how this works. And you begin to read, why did this work? Should this ever have worked? How is it even possible that this worked? Okay? Did you not? This is what I think when I see my code of whatever half a year ago. But if you, while coding, already write down what your steps are, or even better, or say at the end when you're done with the coding, you find your results, you just jot down a couple of, just jot down what the whole point of these things is. This is something that takes only a few minutes to add. Then you have a much better chance to understand later on what you were doing. Not to speak of all the poor souls who, in case you are really successful, need to understand what you were doing. Okay? So on all these things, creating code that can be understood, creating things that can be rerun, creating things that can be tested. This is all of it. This is all of an investment into the future. If you're really successful, this is going to multiply your impact. Now you're just a poor student. Why should I ever think about having impact in the future? Why should I think about the future at all? Well, the very least you can do is think about your own future. And yes, in a couple of years, and you go back to your code and you need to understand what it was doing. Well, think about your future self and help your future self right now. Because right now, if you invest 5 minutes just explaining what the basics are, then you're going to save your future self a couple of hours understanding what your past self was doing. And that's a purely egoistic motive. And if that's all you need, then you can actually make your code and make your future self much better. And with that, with that, I'd like to close. So if you have something that right now looks like something on the left, it's beautifully written, it's nice, it's fine, it's huge doodle and everything, but I want you to be more systematic in all that, both in your process as well as in your thoughts. And yes, a big set of rules, one single checklist that you can go through for your code all along. And with that, I'd like to close, and I'm happy to take questions. Thank you very much. And we have room for questions. And we should turn off the recording at this point because, well, questions.